now look at some single and double replacement reactions. I've included an activity series and a solubility of ionic compounds in water on this one for reference. Now in the first one, we have solid zinc being added to a solution of lead 3 nitrate. How do I know it's lead 3 nitrate? Because there are 3 nitrates and that gives me a -3 charge, so the lead must be a +3. Now the first thing I want to look for to see if this reaction really occurs. So first thing I want to do is I want to go over and I want to identify where are zinc and lead on the activity series. Zinc we'll find here and lead we'll find here. Since zinc is above the lead, it will in fact replace lead in a compound. So when I rewrite this, I want to rewrite this. It replaces the lead. So the lead comes off, and lead is a solid. So lead will be by itself, and it is in fact a solid. And then zinc will then combine with the nitrate. Now in this one, zinc, when it's in ionic form, will always have a +2 charge. So it will be zinc, nitrates are -1. So we will get zinc nitrate, and this will end up being a 2. And for this one here, you have to decide, is zinc nitrate really an aqueous solution or a solid? Well, remember, even in the solubility rules, you go down below here, nitrates are soluble. So this will in fact be an aqueous solution. So now, all we have to do here is now go ahead and balance. You notice the nitrates stayed together. So when we write this, we're going to have a zinc, we're going to have a lead, and let's go ahead and leave the nitrates together because we only have nitrates that appear on both sides. There's no separate oxygen that forms, which is one of the things you want to look for. So let me go ahead. I didn't want to do that. Didn't want to do that either. Wow. That was a big eraser that I put up there. So we have the lead solid plus the zinc nitrate. I want to put zinc on top. I just want to keep the products and reactants together. We have the lead and we have the nitrate. And let's see how many we have. Here we have 1 zinc on this side, we have 1 lead, and we have a total of 3 nitrates. Over here, I have 1 zinc, 1 lead, looking good, and 2 nitrates. All right, so that's not going to work. We need to have a few coefficients in here. I can tell already. If I double this, if I double the nitrates on the product side, that will give me 4. That doesn't work too well with the 3, so let's go ahead and put a 3 up here for the nitrates, giving me a total of 6 nitrates. All right, that will also give me a total of 3 zincs. Now on the other side, I don't have enough nitrates, so I'm going to go ahead and put a 2 here. That'll give me 6 nitrates, which is good, and it will also give me 2 leads. Well, I need 2 leads on the product side. I'm just going to go ahead and put a 2 up in front of the lead. So now I have 2 there, and I have 3 zincs on the reactant side. I need 3. Notice I left the elements that were by themselves for the end, and that will give me 3 zincs. So it balances quite easily. So that is in fact our final answer. It is the balanced equation represented here with all its states. So that's a single replacement. You got to look at the activity series in order to determine. Now in the double replacement reaction, look down here at the iron 3 nitrate. I have to write this out. So this will be Fe, and it's iron 3 nitrates, as we said before, are a -1 charge. So NO3, there's going to be 3 of them, plus lithium, Li, which is a +1 charge when it's ionic. So Li is plus, hydroxide is minus, charge, so just LiOH. And we want to see, first of all, are these both aqueous? And nitrates, soluble, that's that rule back up here again. So that's going to be aqueous. Lithium hydroxide. Well, hydroxides, that goes down here. Most hydroxides are insoluble except those with alkali metals and a few alkaline earth metals. Well, lithium's an alkali metal, so it's actually soluble. So we would write this as aqueous as well. And let's see if any of these ions get together and in fact become insoluble when they're in solution. So if I combine lithium with the nitrate, once again, most nitrates soluble. So that's going to stay in solution. Now let's switch the other two, iron and the hydroxide. So if we have iron hydroxide, well, it'll be iron 3 hydroxide. We'll keep the charge the same here. Well, iron does not fit rule 5 as far as being soluble. As a matter of fact, it's insoluble. So in fact, iron 3 hydroxide is a solid. It precipitates out. So that will precipitate out, leaving us with the lithium nitrate, LiNO3. So that will in fact be our skeleton equation. And LiNO3 is in fact aqueous, so I'll put that on there. Now we have to balance it. So I'm going to have an iron. Notice nitrates show on both sides, so I'll keep NO3s, my lithium, and my hydroxides stay together on both sides. Over here, rewrite those, iron, nitrate, lithium, and hydroxide. So let's go ahead and start tallying them up. First one iron over here. I have 3 nitrates, 1 lithium, 1 hydroxide. On this side, 1 iron, 3 hydroxides, 1 lithium, and 1 nitrate. Well, we're going to need a little bit of adjustment here with our coefficients. Change my eraser size. And take that out real quick. I'm just going to move the plus sign over so I have enough time for a coefficient here. And rewriting that in here. Plus, leave some room for a coefficient. So let's see what I have. Now, on the product side, I definitely need more nitrates, so I am going to put a 3 in there. I'm going to change it to red so you guys can see these. So I'm going to put a 3 in there. That, in fact, gives me a total of 3 nitrates. It also gives me a total of 3 lithiums as we do this. Now, back to the other side. I have the right amount of nitrates. I don't have the right amount of lithiums on the reactant side. So let's go back and change that to a 3 as well. Gives me 3 there. And that also gives me 3 hydroxides. All right, so it changes that. So now I have 1 iron on both sides, 1 iron 3. I have the nitrates, look good. I have 3 on both sides. I have 3 lithiums on both sides. And I have 3 hydroxides. That is, in fact, my balanced equation for this reaction. And that is my double replacement. The trick there is you have to look at the solubility rules and determine, does a precipitate form, which is the solid? And in this case, the answer is absolutely yes.